Alright, let's do part 2. Okay, so we're going to plot this out. Not plot it out, we're going to code it out, then plot it so we can see the graphs. The first thing I did was I imported all of our standard things, and then I also imported all of the variables, just because that's monotonous and time consuming and nobody wants to watch me do that. So all of these variables are all of the variables given to us. Alright, so first things first. Let's define our functions. We want to define the right hand sides of the functions. Our unknown is the temperature. Or no, our variable's time. Variable's time. Wow. That was almost a goof. Alright, then our two unknowns are the concentration of A and temperature. Easy peasy, lemon squeezy. And then we can go ahead and define some of our little tiny functions here, like K. K is equal to K naught times numpy exponent of negative ER divided by where'd I go? T. Boom, boom, boom. Alright, then we can return our two functions in an array format. It's important. First function is the flow rate divided by the volume. That is multiplied by CA minus CAN minus CA minus K times CA. Boom. Here we go. Second equation is the flow rate divided by the volume, again, times temperature going in, do we have that TA, just TI, minus the temperature, plus the HR times K times CA. That is all divided by rho times C. And then I'm just going to put these in parentheses just to make myself feel better, so I don't get confuzzled. And then that is minus UA We'll do UA. I don't need parentheses there. UA divided by rho times V times C, and then that's multiplied by T minus temperature minus the temperature of the coolant, which we also need to specify. Temperature of the coolant. We'll do the first case first. We'll say the temperature, because the temperature initial is 300 Kelvin. We'll go from 300 Kelvin to 290. So the temperature of the coolant at the end we'll say is 290 kelvins. And then I'm going to double parenthesis this. I gotta add parentheses. I don't trust Python. So now we have both of our formulas in there. We can solve those initial values, initial value problems. So we want the right hand side. It's starting at 0 to T end. Our array, our values are CA not initial values and temperature and initial. We just want this initial, we don't want the other one. We want our, what do we want? Give me the suggestions. Not mode. Method. We want method. We want our method to be redow. And then what's the last part? We want our dense output to be true. I can't spell at all. Interesting. Do I not have it up here? What do you mean solve is not defined? Hold on, let's run these real quick. That was the culprit. Alright, so it printed out. Good. Problem, this is not the right answer. So it means we made a mistake. Let's fix it. Okay. Let's look. This one's good. Down here now, let's check it out. Q times V, good. HR times K plus CA times CA times C, good. I know this isn't doing anything. And then UA divided by rho times V times C times temperature minus. Is it just this? Alright, we're gonna roll with it. If it doesn't end up being right, we'll go back and check. This number's not right. Anyway, we can pull out our solution. Set that equal to a variable. We can then start making our plots. So that we need to specify the x-axis. We'll call it t-plot. And then we can make points for that. np dot lin space. That's going from 0 to t end. We did not specify t end yet, so let's do that. T end is equal to, let's say, we can just say 100 for now. And then that is, we'll say 50. And then 50, okay. 50 points. And then we can pull out our variables. Those are equal to solution of the initial value problem times t-plot. Look at that. Now we need to do fig underscore make underscore subplots. We need to specify rows, 2 calls, 2. Nope. Add underscore sub sub underscore scatter x equals t plot y equals CA. The mode, we want that to be lines. Row, we want that to be 1. Column, we want that to be 1. Same thing for down here. X is equal to t plot again. Y is equal to t this time. We want our mode to be lines again. Our row this time is 2. And our column this time is 1. This needs to be an equal sign. And I spelled subplots wrong. Oh, okay, so let's make that 1. This needs to be 2. There we go. So, as we can see, our first graph here is the concentration, and our second graph here is the temperature. So as the temperature decreases, the concentration of A increases until about where it was. Now it's not going to go all the way back to 1 because some of A is going to be reacted with. That's why it's not going to go all the way back to 1. But it is going to go all the way back to 9.5 because there's not enough temperature to fund the reaction, basically. Now let's see what happens if we raise the temperature by 5 degrees Kelvin. Gotta go through everything here. And you can see if we raise the temperature by even just 5 degrees Kelvin, we have this out of control oscillating reaction. When the temperature goes up, there is enough concentration to just fund an out of control reaction, and that results in exponential growth of the temperature until there's no more there's no more product left for it to react with. Then the temperature will fall back until enough concentration can build back up, and then the whole process starts over again, and it just keeps repeating. Let's see how long this repeats for. Let's do 500. You can see that it just keeps going and going and going. It does start to slow down, but it eventually picks right back up again and repeats. So that just goes to show how important it is to test your systems before you run them, and to make sure that you're staying in your stringent values and not going above or below them.